I'm just waiting for the little beep beep to go on so that I know we're being
Thank you. You can start.
Okay. All right, guys. So welcome. We have now finished. We have gotten through all the work for work, energy, and power. And the best way to prepare ourselves for a final exam is to do final exams. So today we are going to look at November 2018, paper 1, and work energy is normally question 5. So I've pulled up a whiteboard and put it together so that we can see the question. I'm just going to zoom it in a little. There we go. So they give us a diagram and they say it's not drawn to scale. Woohoo! We have a diagram, one less thing to do. Okay, it has a vehicle. The vehicle has a mass of 1,500 kilograms. It starts from rest. Ooh, important word. Whoa, whoa, whoa. Important word. Highlighter needed. Have I got my highlighter? Yes, I do. It starts from rest. Okay. And there is a rough incline at the bottom. And point B is 200 meters vertically above the horizontal. Sure, guys, they've given us a lot of information already. Not bad, not bad. All right. They also tell us that the total work done by force F that moves the vehicle from point A to point B is 4,8 times 10 to the power 6 joules. Sure, lots of zeros there. Okay. So they've given us quite a bit of information. And now we can go to the questions. Okay. Before we start, guys, let's just think, okay? The work done by a force that moves it. What year is this? This is 2018, November. I'll put it in the chat for you, Chetty. So it is November 2018. This is a paper 1, and we are busy with question 5. There we go. All right. So before we start, let's just think about this. Okay, you guys are so like, let's go, let's get the questions done. Let's just think. We have a force that moves the vehicle. So this would be an applied force. And what do we know about applied force? Come on, guys, this is now when you use the chat. Come on, what do we know about applied forces? What type of force is it? Come on, come on, come on, come on. I know you know the answer to this question. Non-conservative, there we go. Well done, guys. So this W here that we had, the work given is a non-conservative work. Okay, and that happens to be why they ask us to define the term non-conservative work. You see how they give us handy hints as we're going along. All right, so we know that it is a non-conservative force. Oh my goodness, that's the next question. So let's start going with these theoretical type questions, and then we're going to get to the applications in just a little bit. Okay, I cheated a little bit. I pulled all the formulas for work, energy, and power in here. I also pulled the exam guidelines in here. Okay, power is there at the bottom, and here's work. All right, so here we have define a non-conservative force. It is a force for which the work done in moving an object between 2 points depends on the path taken. All right, guys, so here is our definition. I'm going to zoom in on it a little bit. It is a force for which the work done to move an object between 2 points is dependent on the path taken. All right, so here is our answer for question 5.1. I'm not going to waste time on writing down definitions. Guys, you need. They want non-conservative force. Carl's asking a question. Whoa. Define the term non-conservative force. Carl, did I just read non-conservative and say conservative? That's very possible. It is a force for which the work done in moving an object depends on the path taken. Guys, am I pretending to be blonde again today? I'm sorry. Okay, so what do they mean by path taken? They mean getting the object from point A to point B. Michaela, I'm quickly going to go back to the diagram and just show you an example here. Okay, so now I know we've got a ramp going up. So sort of the only route that we can take for this car to go up the incline is up the ramp. Okay, but if we really think about it, this car could have driven from A to whatever this point is here, let's say C, okay? And then something could have hoisted it up to point B. So when we talk about path taken, we talk about the actual distance or the actual route that the object travels, okay? So this means that the work done by the force causing the car to go up the incline depends on the fact that this car travels exactly from point A to point B. If the car traveled from point A through the bottom and was then hoisted up to point B, then the work would have been different. Okay, that's what they mean by path taken. Has everybody got that definition, guys? Again, make sure you have these exam guidelines, okay? They are gold. All the definitions you need to know is in here, okay? Make sure you have it. Make sure that you use it, especially when you guys go back to school, okay? That you have this with you, okay? Cool. Let's look at the next question. Oh my goodness, come back here. So the next question is F conservative or non-conservative? Very easy, yes or no. We've already answered that question. F is not conservative, no. Okay, they want to know, is the force a conservative force? So the answer is no. Okay, they don't even ask us for a reason, and it is a little 1 mark question. Okay, cool, nice and easy. Good way to start first 3 marks. Yeah, okay, we got those. Now they ask for the average power generated by force F. Sure, how many marks? 3. Okay, let's think about this. Average power, remember what we used for average power. Let's pull over here and have a look at the formulas. Oh, this one blurred badly. I apologize, guys. P average is equal to the force applied times the average speed. Okay. Do we have any of that? Calculate the average power generated by force F. They give us mass. They tell us the height in which it changes. They tell us the work done is that by force F. Sure, guys. How do we think we're going to attempt this? Is there a time? No. What do you mean? 90? Did I misread a question? Ha! Thank you, Kyle. Thank you, Tobani. Guys, that 90 seconds was hiding there under all your chats and your participations and all of that, okay? Thank you so much for pointing that out to me. So we have a time. So we are going to go easy route. It is 3 marks. Guys, remember when it's 3 marks, it means we don't have to do a lot. It means we're going to get a mark for the formula, a mark for the substitution, and a mark for the answer. All right, so we have time. And they were nice. They gave it to us in seconds. And we have the work done by the force. And now, of course, I can't remember what that value was. Slide up. Ta-da. Sure, Luke, that was quick. I see the questions. I will get to them. Don't panic. I'm not ignoring you guys. 3 marks. Yes, it is 3 marks. What I mean by 3 marks, it is 3 marks for the question. Okay. Ma'am, we can't use the PVF formula. No, we can't because we don't have V. Here they give the speed, okay? You can't use this speed to answer that question, okay? That's cheating, okay? So, you guys all beating me to it, which makes me very happy. You know that. Formula. Substitution. Apologies for writing it next to. I never do that, but I'm just trying to save a little bit of space. And I'm going to trust you guys with that answer because I see a lot of you getting the same answer. Oh my goodness, how many 3s do I have to write? 2 more. What? Okay. Yay, well done, guys. I like it, I like it, I like it. Good job. Okay, so that's 6 marks in the bag, guys. Like 6 marks. Woohoo! Next one. The speed of the vehicle when it reaches point B is 25 meters. I see you, Bob. Just give me a second to just write that in there. Okay. Whoa. Can we write the answer in scientific form? Of course you can. Okay. We have been given that thing there. And we know that it starts from rest. So we know that this is 0 meters per second. Okay. Bob, if you need me to write the answer in scientific form, let me know. But I'm pretty sure your calculator is better at doing that than me. All right. So we now have a speed. State the work energy theorem in words. Oh my goodness, guys. I know you guys don't like definitions. But if you think about it, this question counts 13 marks, okay? That's not a lot, okay? And 1, 2, 3, 4, 5 of the 13 marks is definition and theory, okay? So you've already got 5 of the 13 marks. And come on, that average power, oh, that was easy. Okay, that was super easy. So the only one that could be tricky is this energy principle one. Randy got the definition 100% correct. Well done. So work energy, I'm going to just slide it over here. Okay, work energy theorem. The total work done on an object is equal to the change in the object's kinetic energy. Super duper easy. If you get worried, remember this formula is on the information page. Okay, so you can, if you get worried, you're not sure about the answer, you can go and get this from the information page. All right. Good job, guys. Super, super proud. Super, super proud. Sure. Absolutely love it when you guys work with me like this. Never, ever had a really bad lesson with you. Ever. Like, ever. And that's saying a lot. Okay. Right. Last one. Sure. How do we manage that? We might even have to do another paper. Use energy principles and calculate the total work done on the vehicle by the frictional forces. 5 marks. Okay, not that bad. Not that bad. We're going to get there. Okay, so now let's start thinking first. Okay? And you guys know me, I might have to like delete and carry on and delete some more, but we'll get there. Ooh. Right. So they want to know, their very specific question, the total work done by the frictional force. Okay? So we want to know what work is done by the frictional force. Frictional force is a non-conservative force. Yes, we have a non-conservative force. Well done. Okay. We also know that non-conservative forces cause change in mechanical energy. EP. Okay. And I'm going to expand this a little bit. Okay. So it is half mass final velocity squared minus half mass initial velocity squared plus the mass times g times the final height minus mass times g times, oh my goodness, initial height. There we go. All right. Now we don't know what the total is, but Asake got there flippin' quickly. Okay, well done. Well done. Moi. Ooh, Randy got a different answer. Whoa. All right. Let's see why you guys got different answers. I have a sneaky suspicion I know who did what where. I think we're supposed to use W net equals K. Luke, why do you say we're supposed to use W net equals delta K? I don't mind. Why do you think we're supposed to use W net equals K? I like being corrected and like questioned and stuff. I do. I really, really don't mind. Oh, Luke, now you've gone quiet. Okay. The reason why I'm using non-conservative forces, guys. Okay, Luke, that's not a bad argument. Okay, Luke, that's not a terrible argument. Okay, why don't we, Luke, see how I go, and then Luke, I know how you're getting there. Okay, I can see how you're getting there. So what I'll do, Luke, is I'm going to do it this way and see what we get. And then I'm going to do it your way as well. I'm sorry, you're actually very right. I didn't consider doing it that way. Okay. Because of the definition. Yeah, okay, fair enough. Fair enough. I think you guys might actually be onto something. Okay. So let's see. Let's see. I actually think Luke might just be smarter than me today. Right. What's the mass? Do we have a mass? We have a mass. 1,500. Okay. So 1,500. Final velocity, if I remember correctly, was 25. They say from rest. So that is 0. Thank goodness. Then we know that this vertical height change there is 200. Okay. Oh, I'm going to have to remove that. Dunk. Go. I might have to remove the one below too. You know, I was definitely going to have to go. Here we go. Right. Now I have writing space. Woohoo! Okay. 1,500 times 9,8 times, guys, don't think I just have this problem on a whiteboard, hey? I have this problem, well, on a digital whiteboard. I have this problem on an actual whiteboard, and I have this problem when I'm actually doing it on a piece of paper. I always run out of page, like always. Right. Okay. Right. So luckily that becomes 0 and that becomes 0. And so I can calculate that the work done by all the non-conservative forces, to Boho, I am believing you. Just give me half a second. You guys do realize my calculator skills always need work. 1,500 times 8 times 200. I'm not going to tell you what the calculator just said because then you guys are all going to laugh at me. Okay. I believe you guys. Let me just get there too. Yes. Good job, Wade. Good job, Taboho. Okay. So we get that the work done by all the non-conservative forces, all of them, is 3,408,750 joules. Okay, but this is the work done by the applied force and the work done by the frictional force. Okay. Yes. Good job. Good job. So now we want the frictional force. If we go up here all the way, they give us the total work done by the applied force. And so, no, I don't want it there. Right. So we are going to say 34807 equals, okay, we get given this value for, sure guys, I'm a little bit of a goldfish today. 4,80 times 10, 6. 4,80 times 10 to the power 6 plus the work done by friction. Thank you, Michaela. I appreciate you guys helping me out because my board's so small. Okay, Michaela, don't panic. I think you might have done it the way Luke did it. Okay, so just whoa. And thank you so much for helping each other out in the chat. I can see that you guys have already answered each other's questions. Okay, I really appreciate that. You guys are flipping awesome. All right, awesome, awesome. So I need to get the work done by friction all by itself. So, dum, dum, dum. Okay. Right, Liam, I'm just going to check your answer. You know me. Minus exponent. Where's my exponent? There's my exponent. Yep, well done. Minus 1,391,250 joules. Okay, so if we use, I'm just going to zoom out a little so we can follow the whole thing I did. And of course, I started writing big and big at the end. How do we know me? Okay, so if I used non-conservative forces and the change in mechanical energy, okay, as well as the work done by the applied force, then I get that the work done by frictional force is negative 1,391,250 joules. Okay, a reminder, work is a scalar, all right? We do not interpret that negative. I think in the substitution, we only squared the 25. Which other thing were we supposed to square? Tobani, what else was we supposed to square? I squared the 25 because it's final velocity, and I squared the 0, which doesn't matter because it's initial velocity. Okay. Michaela, yes and no. This value here, okay, I write plus, okay? And this is plus because it's up. And this is total plus, oh my goodness, okay? Also, because the total displacement of the car was up, okay? Tobani, I'm glad you found your fault. Good job. So you could say other way around, okay? But if you look at where I substituted, I end up getting that. Ma'am, is work a scalar? Should I answer the question? 2, positive. That is where I'm getting at, okay? If it is a scalar, you do not interpret this 0. You do not change it to a positive, okay? You leave it as is, okay? Now, I want to tell you something, and if you ever tell any of your teachers I told you this, I will deny it, okay? If you are unsure of whether or not you need to interpret a 0 and turn it into a positive, okay? So we're going, oh, I don't know, vector, scalar, What you do then is you write negative, the value, and you write the unit, okay? And then underneath, and I'm writing it in, let's go rainbow color, okay? Then underneath, you write 139 that, okay, in the opposite direction, blah, blah, blah. When they mark, they stop marking here. They stop marking at the first final correct answer with a unit that they find. I saw this, I marked this, not this question, but I marked work and energy end of last year. And the amount of people that got the negative and then gave the positive plus the unit, and then we couldn't give them a mark. But if you write the negative, your answer, and the unit, we mark up to there and then we stop marking. We don't mark further. We don't get penalized further. But that can only happen if that negative answer has a unit. Terry, I don't know how new you are, but the rest of this group has been doing this. This is now like end of week 3 that we've been struggling through lockdown. So I think everybody's gotten to know each other quite a bit. Oh, I see new faces. Asaki, do you need me to re-explain why you could get away with this, but why you need to write the joule there? How to get away with it. Okay, so how to get away with it. If you are unsure of whether your answer is a scalar or a vector, and you are unsure if you need to take that minus and make it into a direction, the way to get away with it is to take your negative answer and write the unit next to it, okay? And then if you are unsure, to write the positive answer plus the unit plus the direction, okay? Why do you get away with it? Because when we mark from top to bottom, okay, we look for certain things. So we'd look for that formula. We'd look for those substitutions. we'd look for that, okay? And then we'd look for that final answer. The second we have that final answer, even if you wrote this and we weren't looking for it, we'd ignore it, okay? So how do you get away with it? Write the unit, even if you're going to interpret it. Secret of the masking center, you would have wasted your ink. Yeah, no, trust me. Marking papers at the end of the year has meant that I've learned a lot. Okay, guys, and it means that I can give you that information. Okay, so now I promised, because Luke very correctly picked up that do this only work for scalar. You can do it for vectors as well. You won't get penalized, Remo. Okay. So Luke very, very correctly pointed out that they told us to write down the work energy theorem. And the work energy theorem, oh, no, sorry, convention. The work energy theorem says this, okay? And so we should see whether or not we could use the work energy theorem to get to the final answer. Sure, Luke. I know how to get there. We're doing this. We're doing this. We're doing this. We're doing this. Right. So the problem that we have now is we don't know what the network is. However, we have final and initial. So half 1,500 times 25 squared. Don't square the mass as well. Grr. And remember to show the substitution even though you get a 0. Okay. So we get that the total work done by all the forces acting on the car is 468,750 joule. Good job. Okay. Now you guys know me. When I get confused and scared and I'm not sure what comes next, I draw a diagram. Okay, so I've got my car. There's a force, an applied force, making it go up. Okay. There is the frictional force, making it go down. Does the total work only include non-conservative forces? No, Michaela. The total work done is the non-conservative plus the conservative forces. Okay. Now, guys, we have the normal force. And you guys know me. I don't draw friction. I don't draw gravity just as it is. Okay. Because when we're working on an incline, that is useless. Okay. So the motion is up and down the incline. So I can ignore normal and I can ignore the perpendicular force. So the forces that are included in my net force is friction, gravity, and applied force. Okay. I'm asked for friction eventually. Okay. Gravity, remember, mg sine theta. You see, that is why I initially chose not to use this equation, because I don't have theta. Okay. I once got penalized for not stating its statical kinetics of friction. Do you have to worry about that in finals? No. No, you don't. Remember, and I do this at school too, okay? I marked more strictly at school so that you do better at finals. Okay, Luke, and those who did it this way, please will you chat to me like now, quicks? Okay, we've got like 10 minutes left, and tell me, how did you deal with the fact that you didn't have that angle of inclination there? Because not having that angle of inclination there is why I didn't use this one. Yeah, okay, cos 0 when we're working with, when we deal with that, okay, that value can be 0. But I'm talking about how did you calculate the parallel component of gravity? Because remember, we need the parallel component of gravity for the conservative force. We can't just go W net equals non-conservative. Ah, Ivan, distance and then use trig ratios to find the angle of inclination. My man, my man. You went this 90 seconds here and the final and the initial, okay? And then you found that distance and then you used a trig ratio. Yo, Ivan, geez, that's impressive. Wow, sure. Let's have a look at how Ivan did that. Gosh, Ivan, that is impressive. I'm gonna do it here in blue on the side. I'm just gonna throw away that quickly so that I have some space. All right. So guys, Ivan said he went VI equals 0, VF equals 25. Are we going plus? I'm assuming so. And he used delta T as 90 seconds. And then he calculated delta X. And this distance here is delta X. Okay. Sure, Ivan. That is very impressive thinking. Wow. Okay, so we're going to go delta X equals VI plus VF over 2 times delta T. So 0 plus 25 all over 2 times 90. Ivan, did you get 1,125 or am I smoking something? Equations of motion, yes, Tobani. Remember when I said to you guys, this unit can get ugly because sometimes you have to pull 20 million thousand things together. Ivan for president, I like that idea. I like that idea a lot. Yeah, Randy, I agree. I definitely wouldn't have thought of that. Okay, so now we have that and we have that, okay? We need to get that angle there. This is opposite over hypotenuse. Opposite over hypotenuse is sine. So to get that angle, okay, to get that angle, I'm going to go inverse of sine of opposite over hypotenuse. Let's hope that it's a nice number. Better put brackets around it because I don't have a Casio. I get 10,24 degrees. Sure, Ivan, yo, never in a million years would I have thought of doing that. Sure. Okay, guys, let's quickly finish this up. Thanks to Ivan, who got us an angle one I would have never been able to calculate. So we have 1,500, 9,8, and sine of 10,24. Dum, dum, dum. 9,8. Sine of 10,24. Make sure your calculators are in degrees. 2,613,25. Right? So that's that force. Okay. Now we're going to use this oak here and calculate the work done by that force. 613,25. We know it was 1125. And now, Luke, here is your cos 0. There is your cos 0, Luke. Oh, wait. Ma'am is not listening. Ma'am is not thinking. That is gravity. It is down. This 1,125 is up. Guys, Midrand High is not a private school. Midrand High is a government school. I've been at Midrand High. I haven't taught there, but I've been there. Oh my goodness. Okay. So the work done by gravity, 2,939,901,04. Oh my goodness. Okay. Right. I actually think we're getting somewhere now. Okay. Oh, the first method, way more time efficient. Okay. I think that's maybe why this question was so mean. Because I remember a lot of my learners that year said to me, sure, ma'am, we have no clue. Okay. Ivan's making us look bad. Ivan's making me look bad. Okay. I can deal with that. Okay. So we know that the net force, come on guys, we need to push a little bit to get through this example. Net force, okay? We don't know what the work done by the non-conservative forces is. We've calculated the work done by the conservative force, the one that gave us the flippin' headache. Oh, goodness, okay? So work done by non-conservative forces. Woo! Okay, 4, 6, 8, 7, 5, 0. Plus, geez, that's a big number. 2,939,901,06. Non-conservative forces, 3,408,651. Guys, you are testing my ability to say numbers. Yeah, I know. All of this for 5 marks. That's why I picked the first option. Okay, now let's look. Is this the same work done we calculated here? 3,508,750. Not quite, but very close. Can you see that? Here I calculated the total work done by the non-conservative force. Okay, Luke, yes, you are exactly right. Okay, so you would have taken this value plus, where's that big value? This value, the work done by the applied force, okay, plus the work that we're trying to calculate. And that would have given you, I'll see, Luke, as long as you get that. Okay. All right, guys. Guys, it's time. Oh, my goodness. Sure, my brain is dead. I'm reminding you, on the Facebook page, there is a link. Okay. Sure, now I put it in the middle of my chat. There's a link for a Google Forms. I gave it to you again, please. Okay, go do it. I will write this out neatly and I will put it on the Google Drive. You guys know how to get there, africanteamgeeks.com. Okay, and on my Facebook page. All right. Should I download which app? Tobani, ask me early tomorrow because we do have to cut this off. There's another lesson coming after this. Guys, thank you so much. Luke, thank you for making my brain die. Ivan, thank you for saving us. Woohoo! We got it. Well done, guys. Cheers.